Hello and welcome back to another LeetCode problem. Today we're going to be doing problem number 707, design linked list. And it's not super tricky, but you definitely are going to want to know how to design a linked list, and all these operations are going to be useful for other linked list problems you're going to have. And so we're actually going to go through all of the things that are required, and we're going to figure out how we're going to do these things. So first of all, to initialize the myLinkList object. So what you want to do with linked lists, especially when you have links with no nodes, is you want to create dummy nodes either for the start or the start and the end. If it's we're going to create a doubly linked list here. I think they have a choice of you can do a singly or a doubly, and so we're going to do the doubly linked list. So what we're actually going to do is we're going to have a head dummy node and a tail dummy node, and they are going to point to themselves. And so it's going to be like this. And then we are also going to have the number of elements in the list, so we can just call that num. And just make that 0. So what we're actually going to do is for get, it's going to be pretty straightforward. So we're going to have the head, remember, and we'll have some elements. We're going to have the tail. And so there's a few ways you could do this, but we're just going to do a pretty straightforward approach, where we are literally just going to traverse the list. So we're going to say let's say this is, we'll have some current node, and then we are going to traverse the list, and we're just going to have a counter, how many nodes we traversed. And then whenever we get a node we care about, this will be, 1, 2, we would return that counter. So that's how the get would work. Now add at the head. Let's take a look how that would work. So let's say we have the head, and we have the tail. We have some nodes. Again, I'm just going to draw 2 lines representing the pointers, but they're really, 2 pointers. So what we're going to do to add at the head is also pretty straightforward. So we're going to be at the head. We're going to have the element after the head. And to add to the head, simply what you have to do is you have to put in a new element. You have to have the point of this into this. And then the other thing you have to do is you have to break up these 2 things. And you have to just say for the 2 nodes that are on either side, let's make them point to this node. So that's how you would add to the head. Add to the tail would be kind of similar, except we just add here. So we just take the tail in the previous node. And there is an added index. And so to add an index, let's make this a little bigger and delete an index, and we'll look at that. So first of all, let's say we have a head again, and we have a tail, and we have some things. And so you want to add an index. What you do is you want to add before the element add an index. So let's just say this is index 0, this is index 1. These aren't really like that, but that's how it is. That's how it's going to be represented. We're going to have some current node, and so it's pretty straightforward. So if we want to add an index 0, we're going to start at the head, and whenever this current is before the index we want to add, we want to take the current node and the node after that. It's the same kind of procedure. So we break this up, and we make a new node, and then we make these connections. So that's how you would add. Now let's take a look at a delete. So we have a head. We have some nodes again. So we want to delete this node. So what we are actually going to want to do is we're actually going to want to traverse to the node before the node, and the node. Yeah, so we just need the node before the node, which we actually have, because we have the nice thing actually about all these traversals is we have the left and the right, so we don't need to do. So for most linked list problems, you're going to have singly linked lists, and so you would actually have to traverse here and then get that. But the nice thing is, since we have a doubly linked list, we can delete a lot easier because we have the left and the right of whatever we're deleting. So we're going to have a left, we're going to have a right. Pretty straightforward. Then we just I'm actually going to draw the arrows now. So if we have this, let's say this is here and this is here. The nodes we need to delete are the nodes that are pointing to this node, and we need to point them to each other. So we need to delete, or not the node, sorry, we need to take the arrows. So these are the 2 arrows that point to the node, and it's okay that this node is still pointing to other nodes because the other nodes are now this actually does not need to go there. This needs to go over here. And then that needs to go over here. And so even though this node technically does still point to other nodes, because those other nodes never point to it, and we're going to decrement the size and stuff, it doesn't really matter, right? If we have something like this, And even though there is some node that points to these, it doesn't really matter because we're never going to get to this node because nothing else points to it. So that's totally fine leaving it like that. So I think that's all the operations. So yeah, added index, deleted index. And then we're also going to update like our number of nums every time we add and delete an item. We're going to add a 1 and a 2 and so on. That way we could figure out quite easily, how to delete things. Yeah, so it says do not add the built-in linked list. Fine. Yeah. And now another implementation of this could be you could use a hash map with the index being the key and then the actual node being the value, but we can just traverse. I think that's fine. Like we can just traverse to whatever index we want. There are benefits and, downsides to each, and this is only 1,000 values, so it's not that bad. So we can use whatever we want here. Yeah, but if you do want to, if you do get asked, okay, how do I make these insertions, deletions faster and things, then you're probably going to want to have a hash map where you store the index as the key, the node as the value, and then that would probably be that would take more space, but you'd be able to access nodes faster because you'd be able to access them in big O one time. Where here we're going to actually have to go through this whole thing. Okay. But this is kind of like the traditional implementation of the linked list. That's what we're going to do. So start off, we also do need to make, so it's not given to us, so we need to create a class for the nodes. So let's do that. It's pretty straightforward. It only has an init constructor. So self. We're just going to initialize everything to maybe val equals 0, and then we're going to say the next and the previous are none. So previous equals none, next. I believe next might be something special here. Let's just call it this. Okay, let's just do this. Okay, so then for the constructor, so it's going to be self.val equals val. Self.previous equals none. I guess this would technically be previous, but self.next equals next. Okay, so that's going to be the node. So now for the initialize, we need to make a head and a tail. We need to point them to each other. It's going to be pretty straightforward. So it's going to be self.head equals node with a value of, we don't need to give it a value. So then we say self.tail equals node. Then we just say a self.head.next equals self.tail. Self.tail.previous equals self.head. So we have them point to each other, and then we need to also create a number of nodes, so we can just call that nodes equals 0. Okay. So next we need to get the value at an index. Okay, well, pretty straightforward. So if the index is invalid, let's check for that. So if index is greater than num nodes minus 1, right? So if there's 5 nodes, the last index is going to be index 4. Yeah. So just make sure that, yeah. Okay, so this is 0 indexed. So yeah, if this is the case, then we are going to say that this is not possible. Otherwise, pretty straightforward. So we're going to have our current node. Like I said, it's going to be equal to the head. And we're just going to traverse down to the node we want. So while index is greater than 0, cur plus cur.next. So that's how we're going to get the next nodes. Actually, what we want is we actually don't want self.head. We want, I think we actually want this. Because if it's 0, we still want to go to the next node. Right, so if we have a head, and then another node, and then a tail, and we are asked for index 0, it's going to start here. So we do want one traversal to get to this node. Okay. So while index is greater than or equal to 0, let's move. And then so if index is 0, it would do it once. If index is 1, it would go twice, and so on. And I think that's right. Okay. Now we just need to return. So what are we returning? We need the value. So that's pretty straightforward. So that's going to be cur.val. Okay. Add at the head. Add a node before the first element in the linked list. Okay, so remember when we add at the head, we need the head, and we need, like, if there's some other values, we need the head, and then we need the value that's after the head, and then we're going to change those pointers. So we need the value that's after the head. We already have access to the head, so let's just say this is going to be maybe self.head, or not self.head. This is going to be like, maybe we'll call that the first node or something, right? So just say first node equals self.head.next. Okay, there we go. Now we need to create a new node, so we're going to do that. So new node maybe equals node. We're going to give it a value, so val, and then we are going to give it, so its next needs to be, sorry, its previous needs to be the head, and then its next needs to be, I do think actually this next right here might be a problem. I think this is like a special thing. Let's actually use this instead of next. Oh no, actually it's fine because we're just yeah. No, I think this actually be fine because even if it is a special function, we're just redefining it, so it's totally fine, I think. Okay. Well, if we have any errors, we'll fix it. Anyway, so then we need to what do we need to do? We need to, oh yeah, put the next value of the new node. So the next value in the new node is going to be the first node, right? So if we're at the head and we have some value here, this is going to be the first node, and we're putting in a value here. The next value of the node we're putting in is going to be this, and then the previous is going to be the head. Okay. So this is going to be first node. And then this is going to be head self.head.next and self.firstNode.previous equals new node. Okay, so we just made those pointers. We're good. We also need to increment the num nodes. Self.numNodes61. We don't need to return anything, so we're good there. Added the tail. Pretty similar, except now instead of the first node, we need last node. So node is going to be self.tail.previous. New node equals value. So its next is going to, or its previous is going to be last node. Yeah. So its previous is going to be the last node, and its next is going to be the tail. So, okay, self.tail.previous. Then we have self.lastNode.next equals new node. Okay. So add at index. Add a node, the value val before the index. Okay, if the index is greater, so this is kind of similar where if the index is greater than the length, so if index is greater than self.numNodes, let's return, let's just return. Okay, so we need to add before. Okay, and so when we add before, so let's just redraw some of this. Let's say we have a head, we have a tail, we have some nodes. Okay, and let's say this is node at 0 index, this is node 1 index. Let's say we want to add at like index 0 or index 1. So what we're actually going to do is we're going to start here, we're going to move up here. And this is what we need. So we need to actually access here. We don't have this value directly because, like I said, we're not doing a dictionary implementation. So we need the node right before this, this node right here. And then that way we can get, yeah, if we want to add before, then it's going to be pretty straightforward because we're going to have these two nodes that we can just have it point to this instead of to each other. Okay, so let's do that. So, yeah. So while index is greater than 0, we need to have a cur. So cur equals self.head. And then this is going to be cur equals cur.next. Okay, so now we are at the node before, like the node we want to add. Yes, that is right. So 0 would be, yeah, if the index equals the length of the linked list, node would be appended to the end, and that's what it would be here, I think. So if the index is like 1, actually, yeah, so sorry, the length of this list is 2, so if this was 2, it would go here, and then it would go here, and then this would be, and then it would be inserted right there, which is what we want. Okay, perfect. Okay, so now we kind of do the same thing where we do maybe next node or something equals cur.next. And then so we have the cur.next. Now we make a new node again. Same story. Equals node with a val. Its previous is going to be cur. Its next is going to be new node. Okay, and then cur.next, new next node dot previous equals new node. Okay, now delete. I delete the index if the index is valid. Okay, so if index is valid, like let's say there's two nodes, it'll be index 0 or 1. So I think if index is greater than self.num nodes -1, I believe, right? Yeah, because like if there's two nodes, then the last index is 1. So this would be 1. Yeah, okay. We also did forget to increment here. Okay. Did we have a deleted tail? Oh, there isn't a deleted tail. Okay, so there's added tail, there's delete. Yeah, okay, so there's added index, delete at index. Okay, so to delete at index, we need to get, once again, the node before the index we're deleting. And so how would that look? Let's say, once again, we have a head 0, 1. Let's say we want to delete at index 1 here. So we would start here. So what we want to do is the same thing. While index is greater than 0, we want to move up 1. So now we're here. So yeah, we want the node before the node we're deleting, and then it's pretty straightforward. We just make this point to this point to that, and then that's deleted. Okay, perfect. So same thing, while index is greater than 0, cur equals cur.next. Okay, now we want the node that's 2 nodes after current, because that's the one after we're deleted. So next node equals cur.next.next. Now we just do cur.next equals next node. Next node dot previous equals cur. Decrement here. Okay. Yeah, let's see if this next actually gave us an error or not. Find out. Might have to rename it to something else. And yeah, see what happens. Hope for the best. It's going to be annoying to debug. Okay, we hoped for something. All right. Let's actually move this to the other side. So this is just return if the index is invalid. Self.first node dot added head. My linked list object has no attribute first node. Ah. This is a real painful one to debug. for sure. Oh, so we never actually decrement index. Probably didn't do that and some other stuff. Definitely for an actual interview, I would definitely double check all this code, but you know. Cur. Man, how many bugs can I make? Too many. Oh, it never ends. Never ends. It is getting comical. We're just making a bug everywhere we go. Please? Ah, dang it. Let's take a look. Sad. Okay, so we add at the head. Let's see here. So we have a linked list. We add at the head. One. Maybe we should draw this out. Definitely good to look over, but let's take a look. So we have a head. We have a tail. Okay. I do think I want to actually change this value, by the way. So let's do that. Okay. Okay, it still has that error, but that's okay. Anyway, let's see. So add at the head, we are trying to add 1 at the head. Okay, so that would look like this. All right. And then now we're trying to add 3 at the tail. Okay. Null, null. Now we're trying to add at index 2. So adding at index 2 would actually be, so let's actually, oops. So at index 2, I believe, would be at the end. So that would be over here. So what are we actually adding? Add at index, oh no, sorry. We're adding at index 1. Okay, okay, so we're adding at index 1, we're adding at 2. So I think, let's go here. Okay, now we need to get at index 1, so that should be a 2. We did get that, okay. Delete at index. We're deleting at index 1, so we want to delete this node. And then we want to get at index 1, which would be the 3, and we're getting -1. So let's take a look at our implementation of delete, maybe. Okay, well, index equals 0, cur equals cur.next. So if we want to delete, let's say here, at like index 1, so cur starts here. Okay, cur equals cur.next. Yeah, looks good to me. Okay, now next node equals cur.next.next. Yep, cur.next equals next node.previous equals cur. That should be deleted, I think. But yet we are returning -1. Self.num nodes, we did also do that. I am curious. Okay, so we didn't print it. So how did we return -1 is the question. Did we return... Wait a minute. Oh, no, this is a get. No. So this is fine. Let's take a look at our get. Okay, so our error is actually, after missing it forever, this. Nice. Okay, so let's talk about the time and space complexity. And this is definitely, like I said, this is another great one for you to try out because lots of debugging, lots of errors. Definitely would encourage you to put this up yourself. And so here it's time and space. So for, let's think about it. We can just do the time, we can talk about the time and space for every single function. So O of get will be O of n. O of added head would be O of 1. Added tail is O of 1. Added index is O of n because we have to traverse to the index. And so that's the downside of a linked list, is you do have to actually get to the index. Added index, yes, that's O of 1 or O of n, and deleted index is also O of n. So like I said, if you do want a faster data structure, what you could do is you could make a dictionary, and then every time you add a node, like let's say you have some nodes, you would just figure out, okay, what index is this being added to, kind of, and then you can store that in the dictionary, and that way these lookups can be O of 1. So like this deleted index can be O of 1 and things like that. Because like let's say you want to add an index 0, if you know like what node is index 0, you can just call that node directly from the dictionary and so on. Same thing for the gets. So all these would be O of 1 if you wanted to do that. This is a small input, so I didn't do that, but so I'm kind of doing the standard linked list thing. But if you want to do the more complicated one, then definitely I'd encourage you to try using a dictionary. For space, let's think about it. So, I mean, I think it's just pretty straightforward. Like it's just O of n, where n is like the max nodes we're holding at a time or something. Like we just have one linked list. We do have a head and a tail, but those are just one thing. So this is O of n, where this is the number of nodes, and then these times are also O of n, depending on how many nodes you have in your linked list at the current time. Okay, so that's all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.